Good morning. Today we will continue correspondence analysis. Correspondence analysis CA. Last class we have seen the CA process model, then CA steps, then with an example we discussed about four questions that can be answered through CA. Then here we have defined row profile, column profile, then chi-square distance, and we were about to start the singular value decomposition. Singular value decomposition. So, today we will discuss from singular value decomposition and the example we will continue. Then we will discuss how perceptual maps can be created, then interpretation of the maps, then there are certain numerical measures which ultimately help us to quantify the feat of correspondence analysis, that also we will explain. And then finally, we will conclude from the case study. Okay. So, what I show you now, initially I will again show you the CA process model, then we will straightway go to the singular value decomposition. See the CA process model, what I said earlier, that it has inputs. So, under inputs coming categorical variable, then you are coming contingency table of frequency data. These are input to the process. So, input to the process, and here what you do in under process, you compute the measure of association, then compute fit measures, then you develop or create perceptual maps, and what is your output? Outputs are one perceptual map and two fit measures. This is the model. So, here in this particular first case, they compute the measure of association. We have shown row profile, column profile, chi-square distance. Let us go to now singular value decomposition. Okay. Here let me tell you one more thing, that we are talking about the defect in sheet metal component of a medical diagnostic equipment, and which are supplied by 4 vendors. The components are supplied by 4 vendors. There are different part numbers, different time period, and different categories of defects. And when we compare any two of these categorical variables with the defects data, we will be able to find out this type of contingency tables. As there are 4 categorical variables, so 4 C2, 6 contingency table can be created. And in this lecture, we are basically talking about analysis of each of the contingency table with respect to correspondence analysis. So, there are many questions, actually 4 questions and 4 answers. The last question was that can these relationship, that means the question 3 was what is the relationship between vendors and category of defects. Now, question 4 is can this relationship be represented graphically in a joint low dimensional space. So, the question 3 will be answered through chi-square distance, but question 4 requires some advanced matrix manipulation, that is known as singular value decomposition. And this is singular value decomposition is similar to eigenvalue eigenvector decomposition of a matrix, but eigenvalue and eigenvector decomposition possible only when the matrix is a square matrix. When the matrix is rectangular matrix, that decomposition is not possible. So, we will go for singular value decomposition, which makes rectangular matrix to be decomposed into different vectors and scalar quantities. Now, this is what singular value decomposition. Singular value decomposition is VT. Here we want to decompose the weighted chi-square matrix this is basically chi-square distance matrix D. Okay. So, we want to decompose in such a manner that D will be U S V transpose. Okay. Now, what is U? Now, our D is, let D is our P plus P cross Q matrix. D is P cross Q matrix. For example, if there are 4 vendors, then P equal to 4 and 8 categories of defect, Q equal to 8, then it will be 4 cross 8 matrix. Okay. Now, we will create a matrix here P cross K, where K is the hidden dimensions, latent dimensions, that is number of latent dimensions, you can say number of latent or hidden dimensions that can reproduce or that can help reproducing the matrix D, when multiplied through U, S and V transpose. So, what I mean to say, this K is the dimensions, reduced dimensions. K is the reduced dimension, what we want to know. How this reduced dimension is coming? This SK, S will be your K cross K matrix, then this will be your V transpose, so K cross Q matrix. So, P cross K, K cross K into K cross Q. So, these two will lead to P cross Q. Okay. Now, how do you get this U, S and V? What is this method? Okay. So, I will discuss some steps. So, step 1 is compute D transpose. Now, if D is P cross Q, then D transpose is Q cross P. So, D transpose will be it will be P cross Q into Q cross P, that is P cross P. So, this is a square matrix. So, D transpose is a square matrix. Now, this can be decomposed using eigenvalue eigenvector decomposition. So, can be decomposed using spectral decomposition or eigenvalue eigenvector we will be able to find out. And I have shown you in principal component analysis that when a matrix S is a square matrix, then it is decomposed for eigenvalues, then the determinant of this minus this is put to 0 and we will get a characteristics equation. This is the characteristics equation, and the root of this equation, suppose S is P cross P, then there will be P roots of this equation. So, that means P number of eigen values you will get in such a manner that if eigenvalues are lambda 1, lambda 2 to lambda p, then lambda 1 greater than lambda 2 greater than like this greater than lambda p. This is the eigenvalues. Okay. So, first you do this, find out the eigenvalues, and then putting here in our case here it is D transpose minus lambda I, and you are making this case. Now, D transpose is P cross P we have seen. So, you will be getting P roots, this P eigenvalues. Okay. Now, singular values are the, suppose if I want to know the singular values if I say S j, then singular values are basically the square root of lambda j. Other way, what we can say that each eigenvalue is square of its singular value. In this equation, you will be getting what? You will be getting like this D transpose minus, suppose if you say lambda j I into u j, this will be 0. Once you get particular lambda j, you will put this one is what is u in our case. Okay. So, if there are k hidden dimensions which can capture the variability in D transpose, then ultimately our U total that matrix what we will be getting, that we will be getting EU P cross K. So, from here you are getting the eigenvalues, this is the eigenvectors. So, you will be getting the singular values, and these values will be converted to singular values and eigenvectors to eigenvalues. Then step 2, you compute D transpose D the other way. So, now it will be a Q cross Q matrix. So, if I see my contingency table, this is P and this is Q. When I am getting a P cross P matrix, I am getting in terms of row. When you are getting Q cross Q matrix, you will be getting in terms of column. Now, again you do the same thing, that D transpose D minus suppose gamma I, actually you write lambda I, no problem, that equal to 0. Here you will be getting a Q roots equation. So, ultimately your case will be like this, all the eigenvalues, this one, and using this dt d minus lambda I, then this one is v, this equal to 0. So, you will be getting a v, this is the eigenvector, that is q cross k, you will be able to get. And interestingly, what you will find in the earlier case, you found that lambda 1 greater than equal to lambda 2 greater than equal to lambda p. Here lambda 1 greater than equal to lambda 2 greater than equal to lambda q. So, ultimately if p greater than q, so what will happen? Ultimately that p minus q lambda values will be 0 here, but because of the special structure of the corresponding contingency table, you will find out here that k is minimum of p minus 1 and q minus 1. So, in our case p is 4 and q is 8. So, k equal to minimum of 4 minus 1 and 8 minus 1, that is minimum of 3 and 7, this is 3. So, 3 dimension is enough for our work, because for the perceptual map to be generated, or for the lower dimensions, we are basically trying to reduce the dimensions here. So, k is enough, that is the dimensions, number of dimensions, which will ultimately explain, able to explain the variability involved in the contingency table data. Okay. So, this is basically that means what happened, you can go for the steps provided here for the singular values, and as you will find out that even though we are basically going for eigenvalue, eigenvector decomposition for two different matrix D transpose and D transpose D, but as the square matrix, both are square matrix, and you know that the eigenvalues are same for a matrix and its square matrix and its transpose. So, both the cases you will be getting the same eigenvalues. Eigenvector will differ, because eigenvector differ, the reason is one is in the p cross p case, that is for the row, other one is the column case, though these vectors will differ. So, this decomposition is known as singular value decomposition, and singular values are the square root of eigenvalues. Okay. Alternatively, what happened ultimately, if you use MATLAB, if you give that SVD, suppose SVD D, you plot write down like u and v and something, this equal to this SVD D, there is some changes maybe, but SVD D in MATLAB will give you all those things, USV. So, once USV is US as well as U or S as well as V is known, then you can go for obtain row PCs and obtain column PCs. PC means principal component. Now, P is dr to the power half U and D. I think now you know what is your dr. Dr is basically when you are making a contingency table, this side is row mass, this is column mass. Okay. For our case, here there are 8 and 4. So, 4 values here, 8 values here. For row mass there are 4 values. So, our dr, if we are creating like this, all these values, these are all diagonal values, and off diagonal are put 0. So, dr is 4 cross 4 matrix. Where from you get these values? These values you will be getting from contingency table, when it is ultimately made converted to correspondence table or correspondence matrix. Similarly, DC will be 8 cross 8 matrix, where the diagonal element will be this. This value, and off diagonal element will be 0 again. Okay. So you know now. So you now know that what is dr half. Dr to the, we have to create dr to the power minus half. So you are making inverse of dr and then square root of each of the elements. If you do this, then the principal component for the rows, this will be dr half u d. Already you have computed E, d you know this is the T. Similarly, the principal component for the column, if we say q, that is dc half v d. Okay. So you are in a position to compute the principal components. See, the beauty of this correspondence analysis, it started with nominal data which are cross classified, and you are getting a frequency table, and you do not know that from frequency data how to get the distance, similarity, all those things, difficult one. And then what is the intelligently, what it is that the coordinates are created, and using weighted chi-square distance and singular value decomposition method, you are able to extract different pieces, principal component. This is a wonderful development in that count. Okay. Now, once PC is developed, for example, in the table we have given you the contingency table for vendor versus category of defect, you see we have extracted 2 PCs here, but the k is minimum of p minus 1 and q minus 1, which is 3. So, one more PC can be created here, but we have not created, we have created only 2 PCs, and you see the inertia. What is inertia here? Inertia is similar to variance explained in principal component analysis. What we have talked about? We have talked about the lambda value, lambda j divided by sum total of lambda j, this is into 100%, this is the percentage of variance of the x variable explained by that jth PC. Here the similarity, here we use the word inertia. Inertia talks about that what is the percentage of variability in the data set is explained by principal component 1. So, inertia for PC 1 is 95.6 percentage, for PC 2 it is 3%, then rest will be that total will be 100%. So, rest will be by for PC 3. Now, if I go by that cumulative percentage explained by PC 1, that is 95.6%, and if I include PC 2, this will be 98.6%, but 95.6% itself is a big enough. So, that means we require only PC 1 to explain the coordinates related to V1 to WL, that is basically the variability what is present in the contingency table. We do not require PC 2, PC 3. So, that means essentially what happened here, essentially it has happened that although there are 4 vendors and 8 different categories, these different dimensions now, ultimately using one dimension, that is principal component 1, we are able to explain the variability present therein. It is a beauty. Okay. Now, let us see some more slides where we are talking about the perceptual map. Okay. You see the position of each of the vendor and category of defect. You are able to see that this horizontal line, this is the principal component 1, and this line is the principal component 2, and this is component 1, that is why component 2. So, although we are plotting using this bivariate type of bivariate plots, but if you see the position of each of the categories of the row as well as column variable, you see that all of them are very close to principal component 1. So, if I go by the traditional way of understanding, conventional way of understanding, that means along the principal component 1, all the points lie and the variability from here to here. So, this is the total variability, but if we consider the component 2, then you see that there is hardly any variability along this component 2, if I consider these are all data points. So, that is what is justified by this 3% inertia. That means 3% variability of the total data set, in this case vendor versus that categories of defect table. So, that 3% variability is explained by PC2, we do not require. We can only plot component 1 and see this. So, PC1 able to explain the totality of this particular contingency table. Now, how do we interpret this? That what is that PC1? What is the name of this PC1? So, by interpretation we want to mean that it is similar to factor analysis. You are getting a factor and you have to have the ability to name the factor. Unless you name the factor, you cannot think that you have done the job correctly, because you have to take decisions for improvement, for betterment. So, I have a hidden dimension. If I do not know what is this hidden dimension, then I cannot improve on the basis of this result or on the basis of hidden dimensions characteristics, because I do not know what is that dimensions. So, let us see how we can do this. So, I will straightly go to some of the fit measures, then I will come back again for the interpretation. See, in correspondence analysis, inertia is a important measure. Now, what we say inertia means, that is the percentage of variance explained. When we talk about inertia of a component, that means the component extracted, what is the percentage of variance the component is able to explain. Okay. Now, when we talk about inertia for each of the categories, that means it is basically the variance or variance part that contributed by each of the categories to the total your variance. Okay. So, in that count, this is 1, and mass you know, that is the total that row mass, column mass you have seen, and quality is basically the quality of presentation in the perceptual map, but more important thing is this correlation value, because this correlation value talks about how good this component 1, to explain the each of the variable categories contribution towards explaining the variability or the variance. So, you see that it is basically the component 1 is able to explain the variability along these, because 0.860, 0.802, 0.872, 1, that means component 1 is enough to capture all the vendor categories variability. Similarly, if you see these column categories except whole missing, all other cases you see the value is quite high. You go to contribution, this contributions also, the another one is the contribution. First one is basically component, how it is able to explain these things, and by contribution what we are saying, how these individual categories are, what is the contribution of individual categories in building this component 1. Correlation means how this component 1 is able to explain or correlate each of the categories with these dimensions, and coordinate is nothing but that piece coordinate values what you have gone for principal axis, that principal component the coordinate positions. Okay. So, using this contribution and correlation you will be able to explain the variable categories with respect to the particular principal component. With this, let me come to this some interpretation. Vendor 4 position is far away from other vendors. You see, vendor 4 is here, other vendors are here. So, that means I can say vendor 4 is distinctly different from other vendors. There is something different in vendor 4. Other vendors are very close with respect to categories or observations of defects. Bend, dent and deburring defects are far away from fastener installation and welding. Bend, dent, fastener installation is here, whereas bend, dent is here. They are distance apart. Vendor 4 has more problem with fastener installation and welding defects. How we can say? Because vendor 4 they are close, and welding vendor 4, so and but vendor 4 versus these are far away. So, relatively we can say vendor 4 has this type of defects problem relatively more, not absolutely. Vendor 1, 2, 3 have relatively more defects related to bend, dent and deburring. The points close to the center of the distal no and significant differences. Those which are coming to this, their difference, because they are overlapping on almost on the average profile. So, there is little differences. Now, if we see the correlation, we are able to find out that each of the categories are being explained by principal component 1 except one categories. Okay. Now, let us see that, as I told you, that overall fit measures total inertia explained by each of the component extracted. This is one measure. Total inertia is defined as the weighted sum of squared distance from the points to their respective centroid. So, you have seen, suppose one point here vendor, this is a point, and then the centroid is this one. So, now what we are saying that weighted sum of the squared distance from the points to their respective centroids. Inertia explained is similar to explaining the percentage variation by R square in regression. The number of components to be extracted is decided based on cumulative percentage of inertia explained, similar to principal component analysis, so 90%. For the case study, 98% of the total inertia is explained by two PCs, while PC 1 alone explained 95.56% of the total inertia. Inertia accounted for by each of the vendors as well as categories of defect, that also I have explained. contribution of vendors and categories of defect to the PC extracted, that is what is contribution. Now, inertia of a point, each of the vendors or categories are explained by PC, that is what is correlation. So, this correlation is very important measure. What is correlation? Inertia of a point explained by PC. Suppose this is vendor 1, its inertia is 0.140. Now, what is the ability of component 1 to explain? That is 86.8% of this inertia is explained by principal component 1. So, that correlation is very big issue for naming the component. Okay. And then what is the contribution? Contribution of vendors and categories of defect PC extracted. That means, what we are saying, this is what is talking about when you extract PC 1, how these categories are contributing in extracting this. Okay, this is fine, but another thing is this one, the categories of categories are one the principal components are extracted. So, after that how this principal component is able to explain the variability of each of the categories, that is correlation. Got it? So, we have to, I am coming to the interpretation of the principal component. Okay. So, let us see that component 1 explain 95.56% of total variances accounted for by the vendors and categories of defects. Here we have used the two things, contribution as well as your correlation into consideration. PC 1 is defined by vendor 4, fastener installation, bend and end, based on these are the contribution. But if you see the correlation, see vendor 4 correlation is 100, bend end 0.99, deburring 0.99 and fastener installation 0.998, again plating 0.99. So, these are the variable categories which are ultimately explaining this, naming this. So, with this what I can say, ultimately we have gone to the the plant where from we have collected the data and we have discussed that what could be this principal component 1. See, principal component 1 is fine here, but naming the principal component 1 or as such component 2 or 3, it requires domain knowledge. So, that domain knowledge, the practitioners, the expert in this particular subject area will help you to understand what this component is talking about. Okay. So, naming a PC extracted calls for the analyst knowledge about the functioning of the system under consideration as well as variables interaction effects. Discussion with plant personnel reveals that a vendor 4 uses all manual fastener installation machine, whereas other vendors use a mix of automatic and manual machines. And when we talk about the defects, the expert says that it is this difference which is making this type of realization. As a result, what happened? We have given the name PC 1 can be named as level of mechanization. Okay. So, if this axis is level of mechanization, so from mechanization point of view, vendor 4 is manual, whereas these are semi mechanized or to some extent some cases semi mechanized. So, as a result, this distinction is happening here. Okay, this then as it is manual, that fastener installation, welding, scratch, all those things are also coming into consideration, but you require exploring it further, that whether some other explanation possible or not, but to some extent it is basically the same thing, that level of mechanization can be given a name to the PC extracted here. Okay. And it is certified by the company people. Getting me? So, this is one use of correspondence analysis I have shown you. I will show you another use of correspondence analysis what I have done. That one is a derailment data analysis. So, we have considered a case of steel plant, and the steel plant has in plant railway system, within plant for their material handling of the raw material, then material handling of liquid steel, material handling of finished products, finished goods. Okay. So, what we have done ultimately, we have considered that shift, then the department responsible, then the causes of derailment, and one more variable we have considered, 4 variables: department, shift, causes of derailment, and line, where the derailment taken, location of derailment. Okay. Now, derailment is basically these are wagon or rail derailment, that at the rail, that in-house in-plant railway track systems. Okay. So, what will happen? Even again there are 4 different variables or 6 different contingency table created, and then finally, we have done the similar way analysis. Ultimately, what we have found out that we have created several rules of derailment. After extracting the PCs, and then when we have given the name of PCs, then we found out from by naming the PCs several things. One is label of movement, that is very important, but which was not nowhere it is there, because they are not also capturing the label of movement data, that how frequently or duration, how long this movement is taking place, this type of data they are not capturing, but from CA we found out this one. Okay. So, label of human involvement, then we found out that the basically the management types, another dimension, that means whether it is actually in the mainly the raw material and liquid steel material handling is managed by the in-plant that company, but finished good that railway tracking all systems are managed by the external company. So, externally managed wagons and internally managed wagons, their derailment pattern is different. Then that criticality of movement, So, we have started with these 4 categorical variables. Ultimately, we landed up to these root causes. So, this transformation was possible only through CA, but to come to this stage we require a lot of domain knowledge, otherwise you cannot. Getting me? Fine. So, you will be, if you go through marketing research, you will be getting a new innumerable examples related to use of correspondence or application of correspondence analysis, and its use in engineering studies also available, but not that in that much. Social sciences cases huge application is available. Okay. So far we have talked about cross table or contingency table of 2 variables, obviously categorical variables. So, categorical variable 1, categorical variable 2, V 1, V 2. What will happen if there is one more categorical variable? Actually, that is all the cases in my example, all the cases there are more than 2 variables. The either derailment or the defect that is occurring with based on the influence of all of the categorical variables, not necessarily that 2 at a time. So, if this is the case, then just going through only bivariate case two categorical variable, taking 2 categorical variable and doing simple correspondence analysis, simple CA will not serve the purpose fully intended for. Fantastic, simple CA is good, it will give you some good idea. Most of the time what will happen, because this CA is used to find out the root causes. So, if you develop several contingency tables and do this, you will be finding out overlying root causes or overlapping root causes. So, then the final set will be distinct causes like this. But why should I go for this? Why should not I consider all the categorical variables simultaneously? Then what will happen? You will be creating nested contingency tables. Correct? Nested contingency table. So, if you include more than 2 categorical variables in correspondence analysis, simple QCA will not work. We have to go for multiple correspondence analysis. What will happen then? This multiple correspondence analysis consider all the categorical variables with their categories, and there will be nested this table and there will be a large number of cells. For example, if category B 1 has 3 categories, categorical B 1 variable has 3 categories, B 2 variable have 4 categories, then it is 4 into 3, so 12 cells. But again, if B 3 is having 10 categories, then 12 into 10, 120 cells will be. If your data size, sample size is small, suppose you have observed 100 cases, then you do not get 120 cells having cell counts, having frequency. So, the more variable you add, more number of cells will be generated. So, more observations are needed. This is one aspect which you have to look into while going for multiple correspondence analysis. Otherwise, what will happen? You will put values to software, software will give something, but there will be erroneous results. Another difficulty while going through multiple correspondence analysis is, suppose the categories are such that there will be some structural zeros. Like if variable category 1 is age and this one is experience, suppose if I say that 18 to 30 is the first category of age and like this, and experience, let this is greater than 20 years. So, the person having this much of age will not have this much of experience. So, as a result, the cell 1830 and greater than 20 years of 1830 years of age and greater than 20 years experience always have 0 counts. This is what is known as structural zeros. So, if this type of things are there, what will happen ultimately? Ultimately, if it is there, you have to look into these things very carefully. Structural zeros. Okay. Another issue related to your correspondence analysis, which you have to keep in mind also, that correspondence analysis tries to measure not only the difference or similarity between the row or column categories, but also association between them. Correct. So, if row and column categories are independent, row variable is not dependent on column variable. So, association you will not find out. So, that then if there are 4 variables, 6 simple CA possible, but what is the need of doing 6 simple CA? If some of the CA, that contingency table, have no relationships between row and column variables, you can avoid this. For example, we have done here like this. There are 6 models possible, but using chi-square test, what we have found out that row and first one, vendor and category of defect, row and column categories are dependent. Vendor time periods, vendor part number, they are independent. So, no need of going for M2 and M3, no correspondence analysis is required. Where there is dependency, then you go for correspondence. That is why we said M1 indicates that CA will give better insights. Not M2 and M3, these chi-square values are very low. So, compared to M2 and M1, M1 definitely gives better insight. So, when there is that dependency is available, then only you go for. So, another issue, suppose if you use MATLAB, many a times straight away this SVD function you apply, you will get that this there will be a difficulty, k is minimum of this, but you will get even k minimum of this, that if it p minus 1 is the minimum, then even pth some value also you will get, what I have seen while using this. This is because of the all the rounding errors, effects, calculation, computational problem. Okay. Then another issue here is that suppose many a times when you go for multiple correspondence analysis, so you will find out that the two principal component cannot explain the variability, desired variability to be explained. This will not happen. I have seen that two component are able to explain around 24, 25 or 30% of variability. So, that means you require more component, then ultimately your purpose is not served. So, in that case what to do? Can we just stop there, or there is some other way of doing things? I think I have seen some papers where they said, okay, you extract as many PCs as possible, PC1 to suppose PCK, then you can go for clustering using these PC values. These are all categories 1, 2, there will be suppose M categories. Then for all M categories here, PC1 coordinates are there, PC2 coordinates are there, PCK coordinates. Sorry, extremely sorry. So, in that case what happen, if I go for clustering, we may find out that values may be okay. So, clustering may help us to find out, okay, this is one cluster, this is another cluster, this is another cluster. So, you will be able to group them. So, what I am trying to say then, that why can't we go for CA with clustering. It is available also. So, similarly other variables can be. Now, I will finish today's lecture with this reference as well as the code. You see the reference for correspondence analysis, Greenacre M 2007 correspondence analysis in practice. That this is a very good book on correspondence analysis, and this is a very famous quote from Abraham Lincoln. The things I want to know are in books. My best friend is the man who will get me a book I ain't read. And that is what is also true, very much true, because it is not because of it is said by Abraham Lincoln. He is a famous great personality, whatever they will say, definitely that has value. But we being ordinary people, when we realize this and do something, we are immensely benefited by these great personalities. And I have seen, because that I have to find out first this book, and I have gone through this book. So, similarly for all the topics covered in this multivariate statistical modeling course, let me tell you very important things here. Your work will be simple if you collect the good books. I suggest Johnson and Wichern book, Johnson and Wichern multivariate data analysis. There is another wonderful book by Hare et al. That is for the research scholars, for the concept building. This book is very good. There is book by Anderson also for multivariate. Then Press, suppose for structural equation modeling and all those things, that Lisrel software, then Gyroscope and Sorbom. You will get that correspondence analysis, Greenacre. You will get couple of good books on factor analysis also. So, your work is first find out the good books. Okay. Another important issue is data. So, theory is one thing, fine, but if you do not apply these theories, whatever you are learning with real data, your knowledge will not be 100% perfect. The reason is because when I applied the different models in the real data, what I found out that surprisingly my expectation meets only 50% of in less amount of time. Most of the times we are finding out that what we thought of and what we are getting from the analysis is not matching. This is because most of the models are developed based on several assumptions. One of the big assumption is multivariate normal distribution. But how do you know that is multivariate normal or not? Many a time this normality assumptions violated, but because we know how to use the software, without bothering about all those things we use and we get some results. Sometimes they are favoring, sometimes not. When they are favoring we are using, but maybe we are using wrongly. That favor is a wrong favor. Okay. So, I say that one is data, and thus another important issue is this data, how you are collecting the data collection process. In the first class, I told about this different study. Data collection process should be governed through a adequate study design. You must know what is your purpose. So, the study design will be governed by purpose, and your purpose definitely will be governed by the problem. What problem at hand? So, your data, then data analysis, then you are getting the results, but this result ultimately solve the problem. Getting me? So, these issues, these are the very key issues. Basically, knowing one issue is okay. All the models we have basically come across several models, starting from basic statistics, under this descriptive statistics, then your inferential statistics, multivariate statistics, multivariate descriptive statistics, inferential statistics. Under inferential, you learn Hotelling T-square for different group categories. Then you have gone through ANOVA, then you have gone through MANOVA, you have gone through regression, you have gone through PCA, you have gone through factor analysis, we have introduced structural equation modeling, we have seen cluster analysis, we have done CA. So many things, okay, but essentially whatever we have discussed in this course, they are very much introductory in nature. Every topic has inbuilt in-depth mathematics, and if you all are interested to know the in-depth mathematics behind it, then you have to go through further good books. For example, Johnson and Wichen is a good book, but how the parameter are estimated, what is the optimization techniques applied, what is Newton-Raphson method applied, or when we are using this some other methods, maximum likelihood method, all those things. So, those derivations and those intricacy, some numerical methods, those things also very important in understanding in totality the data analysis or data modeling steps, those also required. So, nevertheless, this lecture is basically an introduction to multivariate statistical modeling for the persons who are basically in the application side, preferably engineers and scientists who have data, want to analyze data in the multivariate domain. Thank you very much. For any query whatsoever, this is my email address. jmaiti@iem.iitkgp.arnet.in. Okay, welcome. Thank you very much.